no, I'm not saying black holes don't exist. I am saying that when quantum mechanics effects are taken into account, then the singularity theorem is violated.
I think there's a lot of indirect evidence for the existence of black holes. I think very soon we're going to have direct evidence. We're going to point a bunch of telescopes at the center of the galaxy, and we're going to look for this event horizon, this dark circle.
Black holes exist, but are weird. Okay? There's abundant astrophysical evidence for stellar mass and supermassive black holes.
Afternoon, ladies and gentlemen. Welcome to Bang Goes Another Theory of the Universe. We do get through a lot of theories at this festival, I must say. What we're discussing is black holes, really. Early in his career, Hawking and Penrose, who was here just last weekend, described black holes and claimed that they break all of the known physical laws. So in other words, in our universe are little pockets which don't run according to the laws of the rest of the universe, which is an extraordinary thought. Since then, they've been found at the center of galaxies, but now some leading cosmologists, Hawking's amongst them, are beginning to say they doubt that black hole exists. So are black holes more of a science fiction than a fact? And if so, what's really at stake? Does it do violence to the theory of relativity? Does it do violence to our theory of the beginning of the universe? To help us discuss this, we have our three panelists. To my right, Laura Mersini-Houghton. Nice to see you again. Professor of Physics at the University of North Carolina. Widely covered New Scientist and BBC because you are no stranger to controversy. One of the people who has researched the ways that we can gather experimental evidence for other universes, for the multiverse. And not content with ruffling those feathers, she's now telling us that there may be evidence to suggest that black holes don't exist. To my left, Michael Rowan-Robinson, astronomer, astrophysicist at Imperial College London, former president of the Royal Astronomical Society. He was awarded the Hoyle Medal for his research in cosmology, and has pioneered the technologies now aboard the Herschel Space Telescope.
Well,
and the Planck satellite, is that right?
Involved, yes. Yeah.
Wonderful.
Yeah.
And is it true you were also the PhD supervisor for
Brian May?
Brian
yes,
May.
yes,
Oh,
yes. Very good student.
There you go.
He worked really hard.
I had to bring it up, sorry. And over there we have Pedro Ferreira, Professor of Astrophysics, University of Oxford. You wrote the book The Perfect Theory, yeah. To do with the battles which have already been waged around general relativity. And that book was shortlisted for the Winton Royal Society Science Book Prize and shortlisted for Physics World Book of the Year. I'll ask each of our panelists to give us their views in 4 minutes. I'll try and hold them to that, and then we will set to the debate. If I could start with you, Lara.
So black holes have quite an interesting history. If you think of the first Oppenheimer-Snyder work that used general relativity to show the existence of black holes, and how Oppenheimer had this 20-year-long debate with John Wheeler, who ironically ended up coining the word black hole. And then you think of Eddington and Chandrasekhar. Chandrasekhar again did pioneering work and using general relativity showed the existence of black holes, and Eddington didn't like that a bit, to the point that he called it a stellar buffoonery. And of course, after that, I don't think there is anyone that doubts the existence of black holes, especially with a very important work by Sir Roger Penrose and Stephen Hawking. Things got a bit tricky after the discovery of Hawking radiation by Hawking in the early 70s. And the reason is because pretty soon people realized that if you use quantum mechanics and therefore obtain Hawking radiation, you end up with a huge paradox known as the information loss. And that's no good because it, in a nutshell, it forces us to rethink this age-long battle between general relativity and quantum theories. If we accept Hawking radiation, which we do, then we have to doubt the foundations onto which the existence of black holes is established because of the information loss. Quantum mechanics has this sacred principle that states no information can ever be lost. In that case, anything that goes down a black hole and disappears down a singularity produces this paradox where all the information, in principle, we could stuff the whole universe down a black hole, down the singularity of a black hole, and lose that information forever. But yet, at the same time, we would use this quantum theory that has just been violated to deduce the existence of Hawking radiation. So, and this debate has been going on for at least 30 years. Many great scientists have tried to come up with different ways of solving it, but the paradox persists. And it seems that we either have to trust quantum mechanics or trust general relativity, or wave our hands in the air and say, perhaps we need that unknown theory of quantum gravity.
Ah, right, we're back to that.
To my experience, whenever we end up with such a blunt paradox, such as the information loss, usually something very basic and elementary has been missed out from the picture.
Right. When you say information loss, you mean the information that's connected with the matter that disappears into
Yeah.
them? Right, okay.
And never comes back, because we don't know what happens
And
to the singularity.
is it your opinion now that the evidence is now against black holes existing?
Ooh, that's a loaded one. So for whatever reason, people have grown very attached to the word black holes. I think part of it has to do with the culture that spread beyond the physics community. So no, I'm not saying black holes don't exist. I am saying that when quantum mechanics effects are taken into account, then singularities, the singularity theorem is violated, and singularities may not exist. What you have instead is some sort of huge, massive object that would have the same mass and gravitational field as a black hole, but it would not have this exotic singularity at the center. In that case, you wouldn't have the information loss paradox.
Look, I mean, if you look at the history that Laura's mentioned, there's an ebb and flow with regards to black holes. So actually, in 1915, Einstein puts out his theory. One of his colleagues solves his theory and comes up with a solution. And let's just be clear what we mean by black holes. We mean a bit of space-time where right at the center, it's spherically symmetric, so it's round. Right at the center, the geometry is just infinite. It's very, very sharply curved. And then a little bit out, there's a kind of a shroud. There's a surface, which is what's known as the event horizon. And stuff that goes into this event horizon can't come out. Schwarzschild comes up with this, and Einstein, he says, this is a solution, but it's very mathematical. And that's kind of been the tenor throughout the last 100 years, is that someone looks again at black holes, comes up with a more physical model, and someone says, well, actually, it's just mathematics. So stellar buffoonery that you mentioned, the Eddington. And I just think there is this ebb and flow where at some point someone disagrees, someone thinks that there's something wrong with black holes. Okay, so that's just going to happen for a while. It all boils down to, mathematical evidence for it is definitely there. It all boils down to observational evidence, and I don't want to rain on your parade. I'm going to let you talk about the observational evidence. But one of the things that I think there's a lot of indirect evidence for the existence of black holes. I think very soon we're going to have direct evidence. We're going to point a bunch of telescopes at the center of the galaxy, and we're going to look for this event horizon, this dark circle. And where basically the telescopes are going to be sufficiently resolved that we're going to be able to take a photograph of it, and we're going to see if this event horizon is there or not. So my answer to you is, I think ultimately it's an experimental question, it's an observational question, and we're going to see if it's there or not. Now, there are various aspects to this. What happens right at the center, what happens to this shroud, and we're debating these bits of it.
So I want to say 4 things. Summary first. Black holes exist, but are weird. Okay? There's abundant astrophysical evidence for stellar mass and supermassive black holes. I'll just say a little bit about those. In my view, the problem is it's Hawking radiation does not really exist. I'll explain what I mean by that. And finally, I want to, if I have time, to say, does modern theoretical physics have a problem? Okay, so general relativity, wonderful theory, immediately had two great successes, explaining the orbit of Mercury, which was an anomaly there, and the bending of light around the sun. But straight away there was this issue of something funny happening at a particular radius, 2gm over c squared, gravitational radius that was in the first solutions. And as Laura says, Oppenheimer and Snyder in 1939 showed that this was the endpoint of stars above a certain mass. We now know this mass is about 20 solar masses. So a star of that mass, when it runs out of fuel, it collapses, the center collapse just keeps on collapsing, and to a point, essentially, a singularity. But what they also showed is this singularity is hidden from view by an event horizon. I just want to read from the abstract of this 1939 paper, which encapsulates all the weirdness, really, of black holes. So they wrote right at the front of their paper, the total time of collapse for an observer co-moving with the stellar matter is finite. And for this idealized case and typical stellar masses of the order of a day, so the whole thing collapses to a point in a day, an external observer sees the star asymptotically shrinking to its gravitational radius. In other words, from outside, we never see the thing collapsing. It just endlessly, as time goes to infinity, it goes towards this event horizon. We never actually see the thing collapsing in. Well, that was a brilliant piece of theory, but it took a while for them to be found. And it was 1964, the first of these collapsed massive stars was found, Cygnus X1. And so in Cygnus X1, we see an evolved red giant star, something like what the sun will eventually become, orbiting around an invisible 10 solar mass companion. Gas is streaming away from the red giant star, falling into a rotating disk around this invisible thing, around the black hole. The gas gets very hot and radiates in X-rays. So that was the first of these that was found. Now, in the same year, 1964, a remarkable year really, Hoyle and Fowler proposed that the newly discovered quasars had been discovered the previous year are due to 100 million solar mass, supermassive, collapsed objects. And this has been abundantly confirmed by observation. So we see in some of these supermassive black holes, again, X-rays is the key. You're going to the highest possible energies because you're going as near as possible to the black hole. Sorry, 1 minute, okay. So anyway, lots of effects that have been, I won't go into the details, but one of the very nice examples is the black hole in the middle of the galaxy. Two groups have seen the stars orbiting around it. You can see a really nice video on YouTube of the stars orbiting the black hole in the middle of the Milky Way. So basically the problem really is not about black holes, it's Hawking radiation. Hawking radiation for 10 solar mass black holes, it takes 10 to the 70 years to radiate away the black hole. And so essentially, whether black holes are evaporating as predicted by Hawking or blowing up as predicted by Laura, is happening so slowly that even over the whole age of the universe so far, practically nothing's happened. No, one photon has been emitted.
All right, well, we do seem to be disagreeing on whether they exist or not. Something exists, we're just not sure whether they have all of the effects of black holes. So maybe what we should do is first of all address, well, what are black holes and what actually goes on inside them according to the standard theory? Would you mind telling us? Because then we'll know what it is that might not exist.
Yes. So what are black holes? It's Einstein's theory of general relativity basically is an explanation for gravity. And his explanation for gravity is that instead of space and time just being this place where you put stuff and stuff interacting according to a force, space-time has a life of its own. In other words, you put stuff in space-time and it warps, it bends. And then you send other stuff through space-time and it feels the bend in space-time. And you've all seen the hackneyed metaphor of the sheet with a ball in. Okay. Now, if space-time has a life of its own, one of the things you can do is you can look at what happens to space-time, for example, if you pull it quite dramatically at a point. Okay, suppose that you put something quite massive at a point, such that space-time bends so much that it's almost like a throat. Okay, what you'll have is you'll have an area. I mean, if you pinch it down, it's like a throat. There'll be a part from which it's impossible for stuff to escape. And as you go down into the throat, you go down. At some point, there'll be a point where space-time is so bent that it's the curvature, how much it's bent is infinite. It's just colossal. So space-time is so a black hole is basically that kind of space-time. You've got a bit of space-time, and you've pulled it out so much that you have this surface out of which stuff can't come, and you've got this point. Now, what happens inside them? Well, black holes can exist. Basically, there's nothing inside black holes. In principle, there's absolutely nothing inside black holes because it's all gone down into this point of infinite curvature where we have no idea what's going on. We don't know because it's infinite. We don't know what's going on there. That's where the laws of physics break down. Or that's where our ability to predict what's going on breaks down. But inside black holes, it's just a bit of curved space-time. There's nothing dramatic inside black holes. It's just at this point. Is that an acceptable explanation?
It's perfectly acceptable.
Right.
Are we then saying that there's little tiny bits inside the universe which don't operate by the rules of the universe?
I have to be very careful when I say that. There are these points where the laws of physics that we don't know what's going on there. The laws of physics, when we apply there, we get infinities, and we really don't know what to do with it.
It's always a bad sign when you get infinities, I think.
It's always a bad sign, yeah.
Well, just to
yes, please.
I think that's right.
Because there's more recent stuff, more experimental stuff, isn't there?
Well, I was just going to say that this business about, the prediction of the black hole is at the centre. There's a singularity. General relativity has to break down there. It doesn't apply in the case of that singularity. And then, of course, there's another singularity at the beginning of the universe.
Yeah.
And the same issue there, that we could, our observations take us back and back. The models seem to point back to a singularity at the beginning, but actually our theories break down before we get to that point. So, we need a bigger theory to get nearer to that point.
Yes, but you were talking about there being the chance now of pointing telescopes up. Is there, from your point of view, more practical experimental evidence or actual data that says, look, these things exist and we understand something about the surface, I assume?
Well, we never, the observations are not actually at this event horizon. We're always a bit outside it. We get closer and closer. We follow the motion of stars or gas into a black hole. Closer, getting closer. But I would say there's no observations that take us closer than 10 times the event horizon.
Let me just disagree with that a little bit, because the whole point of the Event Horizon Telescope is that you will look at the black hole.
This is for the future, though.
This
at
is
the moment.
For the next year or two. Yeah. And what you'll see is you will see this shadow. You will see a shadow, and you will see the stuff. Some of you have probably seen Interstellar. Okay. Some of you have probably seen the picture of the black hole. Okay. And what does it look like? It looks like you've got this black thing, right? And then you've got this ring of light that goes around, which is the gas that's going around. And so the event horizon, in principle, will see that black thing surrounded by everything else. That's pretty close to the event horizon.
It will be if we get to
that's
that.
I think that's the best we'll ever do of actually seeing the event horizon.
Indeed.
Right. And is it a sharp boundary?
Well, the problem is, the Event Horizon Telescope, a way of thinking about it is, suppose you had a camera, which you could take a picture of this thing, and it has 60 pixels across. So, as a 3,600 pixel camera, it's not great. So it'll, look a little bit pixelized, but you'll see it.
But the light is just coming from the inner edge of the accretion disk, which is still quite a way outside the horizon.
But you'll
see the distortion.
But you'll go up to the
gravitational field.
You'll go up to the boundary, and that's the point.
Lara, do you want to
see the shadow?
One thing that we have to explain is what an effective theory in physics is. General relativity, for example, is such an example of an effective theory. Effective theories have a scale, whether it's an energy or a mass, but some constant, some parameter that is built into the theory, but that determines where that theory breaks down. General relativity has Newton's constant, or inverse of that, which would be the Planck constant, the Planck mass. That tells us that the moment you reach these tiny lengths, or these extremely high energies, this theory is no good. It cannot be trusted anymore. You have to disregard it and replace it with something else. That is the case with this singularity in the center of a black hole, this point at the center where the curvature becomes infinite. We are used to infinities in physics. We know how to deal with them. They pop all over the place, whether it's quantum field theory or general relativity. The problem is not the infinity. The problem is that this theory that is responsible for predicting the existence of a black hole is also the one that breaks down at the center where all the exotic phenomena occur, and all the phenomena we are trying to understand and explain occur. So that's one issue. And as you said, it is absolutely correct that if you apply general relativity to the universe instead of a star, then you will end up, if you extrapolate our universe all the way back to the beginning of time, if you like, speaking in colloquia now, but at just before the Big Bang, before everything blew, then you would expect the whole universe to be squashed to one point. So you'd expect a singularity there, this very exotic, strange thing that we don't understand and cannot address with our effective theories to occur. I don't think there is anyone in physics that actually does think there was a singularity at the Big Bang. So what we think happened there is that some underlying theory, a more fundamental theory, replaces general relativity, and everything is smooth, there are no infinities, and that theory won't break down at those regimes. So that's probably what we will, if I had to take a bet, that's probably what we will end up with where the singularities in the center of a black hole are concerned, the day that we understand these objects better. In terms of the timescales, I understand that if Hawking radiation for a reasonable star, a solar mass, would take 10 to the power 73 years to make that whole star evaporate. That is 10 with 73 zeros behind. So that's an outrageously long time. Then it's such a small effect we don't really have to worry about it. While the star takes a day to collapse, but as Pedro explained, if you are sitting very close to the star, you would see that star collapse in a day. If you sit far, far away from the star, that process would look extremely slow, which is the reason why these objects were called frozen stars. So, and the same with the number for the Hawking radiation. 10 to the power 73 is the time it would take for a faraway observer to see that star fizzle away.
Oh, that's crafty.
It's also the same is true for one of these stars orbiting the center of the Milky Way. They also will not see the collapse of the black hole. For them too, the Hawking radiation takes, well, an even greater time. So the external observer doesn't have to be distant, it just has to be not freely falling. It's only if you're falling in to the black hole that you go through the event horizon and see the singularity. And so unfortunately, the only way you can experience a black hole in all its glory is to commit suicide and go in.
But
just going on the tour,
right,
and going near it, like people go to Antarctica, won't work.
Can I just ask you a question? Is it that you are saying that the theory of the evaporation it must be wrong because it was just far too long?
I wasn't saying that the theory is wrong. The Hawking radiation construction is extremely interesting and ingenious. The trouble is it can't be verified because for the real black holes we know about, it's practically irrelevant. There's hardly anything happens. Of course, there could be very tiny black holes. I mean, atomic size or whatever. And these would evaporate, or if Laura's right, blow up in real time. And it's possible that the Large Hadron Collider, this is what they're hoping, they'll see, black holes, these black holes evaporate. So that would be exciting, of course. But at the moment, astrophysics and cosmology do not need such things, and therefore I put my money on them not being found. But
Well, I would not bet my money in either option. But I know from what Pedro is saying that at least in a few years, we will know for sure whether there is an event horizon or not. So that issue of the black hole being just some extremely massive star with a very powerful gravitational field, but nothing exotic in the center, or having something exotic, the singularity in the center and therefore the event horizon around it, that will be settled. We will know in a few years, and then we will have to come up with the explanations. But getting back to the point of timescales, is Hawking radiation too weak? Does it take too long to produce Hawking radiation? So again, that timescale, that incredibly long timescale, is for someone that is observing far away. As far as the collapsing star goes, and the collapse is absolutely essential to producing Hawking radiation. There could be no Hawking radiation without the collapse. That is before the black hole has formed. So that radiation is produced during those stages, the last stages of collapse. Whatever time the collapse takes, that's the time when you're also producing Hawking radiation.
It sounds like you're all saying we're going to have some kind of new theory. Is that really the
What I
case?
just wanted to say is I think there's a little bit of a distraction here discussing the singularity and effective theories and all that. I mean, there are two bits to the black hole. There's the singularity. We all agree that something will break down with the singularity. Okay. The interesting bit is the Schwarzschild horizon. That's where the Hawking radiation happens. That's got nothing to do with effective field theories. I mean, that's just there. It's actually a pretty weak field.
Yeah.
And that's the bit that we're going to see.
It's one of the two there are these two weirdnesses.
Yeah, but this
one is the singularity and the other is the event horizon.
I think
and that's the one that could be observable.
The interesting weirdness, which is it's really there, is the Schwarzschild horizon. And so when you say look for a black hole, for me, looking for a black hole is not looking for the singularity. I really don't care what's happening at the center of because we don't understand what's going on, and until we figure out better what happens to gravity at high energies, it's all made up. But if you're trying to understand, but for black holes, the thing that's really there, has to be there, is this Schwarzschild horizon. And so the question is, will we see it? And so when I talk about the interesting thing about the Event Horizon Telescope, Hawking radiation, this process that you're talking about, it's all to do with this very mild thing, but bizarre, but mild thing that it is nowhere near the limits of applicability of general relativity. It's there. General relativity predicts it.
Are we agreed then that stars are going to collapse? No. They do collapse, and that when they do, they form something that's extraordinarily massive and has an event horizon?
According to Chiara, yes.
No,
because
okay.
the moment you have an event horizon, you are guaranteed to have the singularity in the center. So the two are the same. If you observe the event horizon, you know that there is a singularity at the center.
Again, I disagree. You can construct solutions, and there's a whole literature, because relativists are very creative people. There's a whole literature of singularity-free black holes. You can do it.
That gets even more exalted. The
Yeah,
traditional ones, you have an event horizon, you have a
so-
singularity. The event horizon, the definition is the surface where all the light rays are being focused towards the center.
Yeah, that's fine, but then what happens inside, I really don't care. I mean, it's this event horizon is the thing that we will see, the thing that leads to Hawking radiation.
But depending on what does happen inside, does it have a consequence for the rest of the theories that we say this is how the universe works? Because I think I'm understanding that if it goes to a singularity, then it means one set of theories we're used to work, and if it doesn't, then perhaps they don't work.
I think the statement is, if we understood what happens to singularities at the center of black holes, without making stuff up, without putting exotic, if we understood it, from GR and quantum, we would know pretty much, we would understand what happens at the microscopic nature of space-time. I mean, the whole way we look at space-time is we look at it as this smooth thing, but actually, how does it actually work if you had the most powerful microscope in the world and you could just drill down and see and look at the smallest scales, what does it look like? And if we understood what happened at the center of black holes, that would help us understand what happens to space-time on the whole, on the microscopic scales.
Michael?
Yes, I just wanted to say that actually the singularity that's likely to be more fruitful in terms of new physics and so on is the one at the beginning of the universe. Because what we're hoping is if by miracle string theory suddenly came together into a theory as opposed to a landscape of an almost infinite number of models, then we would hope that it would tell us what happened before the Big Bang, some kind of shadowy quantum world out of which emerged the universe, we're in. It would explain the mysterious dark energy, something that we require in astrophysics, but have absolutely no explanation for. And it would also, I presume, explain inflation, the period we think happened at the very early universe, in which the universe suddenly inflated out to the kind of scales we see in the modern universe. And no doubt it would predict gravitational radiation from those early stages, which we could actually detect with telescopes. So I think the Big Bang singularity, if that could be understood, would have observable consequences. And whereas it seems that with the black hole singularity, nobody's come up with anything that would be a signature of it. We have signatures over the horizon. I'm not so confident as Pedro that we'll get right to the horizon. We'll get closer and closer to it. But nobody's come up with anything that would be a signature of the black hole singularity.
And you mean something that's not just supermassive and not giving out any light, but specifically has this singularity?
Something that shows that gives us evidence of the new physics that we know we would need if there was a singularity inside the black hole.
Right. But it could just be that it's a...
There is no singularity.
Right.
So,
and is there a consequence for that, though, for quantum mechanics?
Yeah, I mean, especially when it comes to something that is more tangible, the Big Bang singularity. If we go along and take that extrapolation of our theories all the way to where the universe becomes one point, so that's the singularity at the Big Bang, we have just closed the door to scientific inquiry, because time stops at the singularity. It does not make sense to ask what was there before, or talk about quantum effects that might have brought about this universe, and anything else that follows. That is part of the reasoning why many scientists do not really think there was a singularity at the Big Bang.
Why does having a singularity mean we can't talk about the quantum rules?
Have you seen Interstellar?
Yes. Yes, I have, and it didn't help. Very entertaining, but it didn't help a bit.
Did you see the time slowing down as you get closer and closer?
Yeah.
It comes to a halt at the singularity. It's just the red shift and the blue shift effects of the very curved space-time.
So if you're saying if there's a singularity, then we can't talk about where
time stops. There is no time before, so you can't ask the question before.
This is what Augustine said in 700 or whatever, when he was faced with the problem of the infinite divine idleness. So he said, what did God do before the creation for this infinite time before? So Augustine solved this problem by saying, time was born with the universe. So there's no before.
Right, so he just wasn't on an extended tea break, there just wasn't time.
But that's not what we are saying is the right way to go either.
But it sounds to me like you're objecting to the theory just because you want to be able to talk about what was there before.
No, I find myself very uncomfortable whenever I'm working with a theory I trust and that theory breaks down. So it's very difficult to make any extrapolations with high confidence if you are completely aware that your theory is no good at that regime. So if you take quantum mechanics into account, and perhaps we should explain what the information loss paradox is and all those things, it's not difficult. So quantum mechanics says if you have a system, then all the information you have about the system, it doesn't matter how that system evolves, but all that information will be preserved in one form or another. We use quantum mechanics to extrapolate that these collapsing stars radiate and they become black holes, but the radiation is called Hawking radiation. That's a pure quantum phenomena. It's particle creation by the curved space-time around this very massive star. Therefore, if we use quantum theory to end up with Hawking radiation, we trust quantum theory. At the same time, we use general relativity to deduce the existence of this object, of the black hole. It is general relativity that says this is how space-time curves if you have this much mass stuffed in it. And you end up with a singularity at the center, this exotic point of infinite energy densities, infinite curvatures. We have no idea what happens there. What we know is that the gravitational pull of this object is tremendous. If you throw stuff down a black hole, it will go all the way to the center of the black hole, where the singularity is. It will be eaten up by the singularity. It will never, no bit of information about what went in will ever come out again. And you can keep feeding that black hole until you stuff the whole universe, and you have lost all the information about the whole universe and never have any way to recover that. So that is the huge information loss paradox, because quantum mechanics says you are not allowed to lose information. But black holes say we can eat up as much information as you wish us to eat up.
So are you saying that black holes present us with this choice that either general relativity is completely correct or quantum mechanics is completely correct, but they can't both be completely correct?
Or, if they are both completely correct, there was something very elementary and basic missed out in this picture.
Aha.
For example, no singularities.
See, he's back with the no singularity.
Well, I was going to say on this information, from the point of view of the external observer, this information isn't really lost. It sort of remains plastered against the event horizon.
You know, it will go all the way into
In the freely falling frame, it falls in. But for us, it isn't lost. It's still there. It hasn't, for us watching, the information
That seems like a
has not
cheat.
actually reached the horizon yet. Nor will it
You mean
ever.
you're seeing those particles in their dying moment?
As
but
Oppenheimer and Snyder said, you watch it asymptotically. Everything, the matter, the information, everything is heading towards the horizon and doesn't get there until an infinite time in the future.
But suppose we are very close to this very massive object in the center of the Milky Way.
If we're orbiting around it, the same thing is true.
Can I just ask, I'd like to move it on to, we've all touched on the fact that it might do something rather disastrous to our picture of the start of the universe. How disastrous would it be if we decide that there's no singularities? I mean, you like it because then we can talk about what happens before, but do you like it?
Do I like it? Look, I like theories.
Would you like it to be true? Would it be beautiful?
I think we all like theories where we can explain everything. If we had a theory where we didn't have singularities and had an explanation for that, you know, it would be wonderful. There are a slew of different proposals on why that you know, different theories on how you might do that. So, yes, I would like it. I would prefer it if there were no singularities.
Right.
But I would like theories. I mean, personally, I would like theories that you could make specific predictions that would allow you to test whether that theory is the correct theory or not. You know, if you have 3 theories for why there is no initial singularity, I would like to know how I would figure out which one it is. Now, the universe may not be obliging. Right? We may not be able to measure the things that we need to measure to test these theories, and that's, I think, one of the problems that we might be facing. There are limits to what we might be able to measure, but that's what I would like the universe to be like, that we could measure it and see if it was.
Right. But if that's the case, would it mean that Hawking and Penrose went wrong somewhere in there?
No.
No, they made certain assumptions.
They made certain assumptions.
They made the most economic. You know, Hawking and Penrose, and you know, there's a member in the audience who played a crucial role in this, George Ellis.
Yes.
They made the most simple, most elegant assumptions about, and they came to the conclusions they came. Right. Now, if you start tweaking those assumptions,
it's always the assumptions, isn't it?
It's always the assumptions.
It's always the assumptions. Which is the wrong assumption then? If there's no singularity, what was the assumption that they'd have to kick out?
Well, it may be that the theory of gravity is wrong when you go to very high curvatures. Right. So that GR is wrong when you go to very high curvatures.
And poof goes the perfect
It may
Einstein
be that
theory.
our characterization of matter is oversimplified. That maybe we typically talk about stuff like this and light and things like that.
I do, yes.
But maybe there's exotic stuff around, which is actually pretty important in these situations that we hadn't considered before. An example that people are talking about a lot at the moment is dark energy. There's nothing like dark energy in our everyday life. Yet it seems to permeate the universe if we take our observations of our cosmological observations on face value. Assumptions like that.
Is it that dire? It sounds like we could end up having to rewrite one or possibly both of the 2 theories which we think explain the physics of the universe.
Well, there's a regime in the Big Bang. There's a regime where they both have to play an equal part, and therefore you need a new theory which combines them. That's what string theory is about.
Yes.
Okay. And I've mentioned that as a byproduct, if that was successful, and I don't think it's anywhere near success at the moment, it might not be for the next 1,000 years. But supposing it was successful,
the look on your face is priceless. 1,000 years.
But supposing it was successful, then I mentioned that we might get an explanation of the dark energy. We might get an explanation of how the universe started and whether it was a before. We might get an explanation of inflation. But there's a couple of other things that...
We've only got time for one of them, probably.
Well, okay, sorry. But it's just that there's a limitation of general relativity applied to the universe, so that it doesn't say anything about the topology of the universe, how things connect up on the large scale. So there's when you're looking in opposite directions in the sky, do they meet up or not? General relativity does not say, and yet that must be an interesting fact about the universe.
When you say meet up, how do you mean?
Well, in other words, if you look indefinitely in that direction, do you see the same objects if you look indefinitely in the other direction? So that's to do with topology, how things connect up on the large scale. General relativity has no prescription, and yet it is a part of the structure of the universe. And it's not to do with the Big Bang. It's just actually the geometry of the universe is not specified by GR totally. And I regard that as a weakness of GR. And so a new theory is needed not just because of the Big Bang, because of the singularity, for other reasons too. I could give other examples, but you say the rest of the time.
Can I just give you the last word? Would you like there to be a new and different theory? And if so...
It's not a matter of like, I don't think any of us has any choice on how nature works, and progress is a step-by-step event, so we can't control what we like or don't like. But I would say that especially theoretical physicists are a very impatient bunch. So rather than waiting for a very long time for that new theory to come about, I think we can still make quite a bit of progress understanding the current problems, open problems and paradoxes with the theories that we already have. And that will also aid us, even if it's a blind man's walk, it will help us choose the right direction towards that unknown great theory of the future.
But you were being slightly more specific, though. You were suggesting that maybe we end up with a theory where there isn't a singularity.
I think so. I mean,
what would that look like?
That's why I brought up the history of the black holes. It would look exactly the same as all the physics looks now. It's the singularities are quite recent in terms of science. It's only from the 1930s onwards. And initially, people found it outrageous that anyone would say, well, mathematically, I end up with a singularity.
Yes.
And then we got used to that. We said, oh, great, mathematically, we end up with a singularity. Then we ended up with paradoxes from the 70s onwards.
But what I mean is, if the universe doesn't go back to a singularity, which I admit is a strange notion, you stuff the entire universe into something smaller than a pinhead, and everyone goes, oh, that'd be fine. If it's not that, what are we going to? Where does it begin? Does it begin with a small piggy bank, or a cloud, or what? I know I'm being facetious, but if it's not a singularity, yes, that's why they're here.
Oh, right. Okay. So I don't think there is many people left who take the singularity of the Big Bang seriously. I think the universe at the beginning was a very small, finite object, and that's our universe.
Finite.
Finite. So no singularities, no infinite energy density stuff to one point. If it was small, incredibly small, that part we know because we can see back in time by looking far away in distance. But if it were incredibly small, it has to be a quantum object. Then we get to, besides the origin of the universe, we get to a more fundamental question, which is the nature of space-time itself. What is time fundamental or is it emergent? If it's fundamental, then we can continue asking, what was there before that quantum tiny universe existed? Was there something else? Are there other objects?
But it has to be tiny and
the answer,
not...
I think, is yes.
Oh, right, okay. But so yes to tiny and no to infinitesimally small. Not a singularity.
Reason to suspect that the universe would have been infinitesimally small.
Right.
I mean, as we all mentioned, general relativity and quantum mechanics are the tools that we use to reconstruct the history of the universe, and they have a scale built into them, known as Planck.
Planck, yes.
So
he crops up always at the end.
Everywhere,
Yes. Could I ask you to thank our three enormous brains for...